In the back, okay. Okay. So if anytime you cannot hear me, raise your hand. Okay. Right now it's maximum volume, so I don't know. I will see. So based on the homework due on last Wednesday, just want to remind you guys for the project. So here's the thing: projects due October 31st. Yeah, Halloween. So because on our homework that was due on Wednesday, we also had one project problem, and as I expected, which I mentioned in the class before the homework due, I said we always have students have computer crash. Of course, the next day I received email that computer crashed and asked me for extension. And also received emails. I think our homework was due at 11:59. I received email screenshots like something went wrong and email me at 11, ask me what was wrong. So I really want to say that it's not that I'm mad at any student and I didn't really want to help. I'm incapable of help. If you just show me the screenshot, that's something like your final result, like there's no displacement, there's no stress. Why? Just by reading the screenshot of your final run result, I cannot fix the problem, because some of you guys came to my office hour. I really need to check every step and also the input file line by line to know which line, which part actually went wrong. I cannot really see like you have one screenshot and I can somehow fix your problem. It's not like I'm unwilling to help at that time. It's really I'm incapable to help. So again, this is just a reminder. Oh, well, that homework is fine because you can drop that homework. It's not gonna negatively impact the final grade. But just reminder of you guys for the project. Highly encourage you guys to work on it early. Do not wait until the deadline and like it's due at 11:59 and email me 11 and then it doesn't work. There's nothing I can help. If Alice, if you email 7 days earlier, I can ask you to come to office hour the next day, right? I can help you check. You bring your computer, I can help you check. And we do have office hour every day. And I also said I extend my office hour from on Monday and Wednesday, so 2 to 4, 2 hours per day. So please work on it early. Don't wait until the last minute. Otherwise, there's no way I can help. And also the computer crash problem. Again, homework is fine. You can use one drop. It will not negatively impact your final grade, but we only have 2 projects. Cannot do like one drop out of 2. So I gave you 1 month to work on the project. You don't need to wait until the last minute and figure out your computer crash or figure out your Wi-Fi disconnected or something went wrong, something go wrong. So just start working on it early and try to submit early. You don't need to wait until last minute of that 1 month time. So in the last class, we talked about the strain for CST element calculation, strain calculation for CST element. So this is the definition based on the mechanics materials, and we had interpolation function for U and V. So that's how we derived the strain, normal strain in the X direction, normal strain in the Y direction, and shear strain. And you can see that it depends on nodal degree of freedom, all the U and the V's at 3 nodes. It also depends on the B and the C. So B and the C, they are the function of, not function, they depend on the coordinates X and Y. So B and C definition are here. And of course, this will be, well, this is not an original equation. Original equation here. This will be provided during the exam. You don't need to memorize anything. So these are B, C, F, and nodal degree of freedom. You can calculate strain. And of course, we put a 3 equation into matrix vector form as is in FEA. So now it becomes this vector equal to this matrix times all nodal degree of freedom of our CST element. And we normally simplify this equation and write as strain vector equal to the B matrix. This is a B matrix times nodal degree of freedom vector. So strain equal to B times Q. This is what it means. And we used the example 1 in the previous lecture and solved the strain in the X, normal strain in X, normal strain in Y, and shear strain. But of course, if in previous step we already have the expression of U and V as function of X and Y, we can use the definition directly. Probably it's easier, save you some time to get the strain in all two normal strains and 1 shear strain. And converting from strain to stress is purely a mechanics materials problem. And since our problem is a plane stress situation, so this is a C matrix for plane stress situation. We normally put this equation, simplify this equation as a sigma vector equal to C matrix times strain vector. So this is purely from mechanics materials. And again, this matrix will be provided during the exam. And we also use that example if we had Young's modulus, if I had Poisson ratio, how to find the stress. Using that example problem, this is the specific calculation. And we started a little bit about the stiffness matrix, for CSG element, and similar as what we did in the bin element. So basically, we derived strain energy for 1 bin element. Here, we derived the strain energy for 1 CSG element. And based on definition, we know that strain energy of 1 element equal to integration of the element. This stress times strain is the strain energy density. If you integrate over the volume, it becomes strain energy in the element. Sorry, there's a mistake here. This should be a vector. Should be a vector, not a matrix. For 3D complete 3x3 matrix, that is but here we are dealing with the plane stress situation, so we put only 3 non-zero term in 1 vector, so it becomes a vector. It's not a matrix. And we also talk about, I just mentioned, strain equal to B matrix times degree freedom. So here, this transpose, remember we talked about in the first class, the preliminary, mathematical preliminaries, this transpose equal to B transpose times, sorry, we need to switch the order, so it should be Q transpose times B transpose. And this one, sigma equal to C times strain, right? That's right here. Sigma equal to C matrix times strain matrix, the one I just mentioned. Sigma vector equal to C matrix times strain vector. So now for this one equal to C times strain equal to B times Q. So it becomes C times B times Q, right? So again, in the end, what we want to do is that it needs to be equal to 1/2 Q transpose, there's a coefficient in the middle, and this Q here. And everything left in between should be the K matrix, right? This is similar, let's say in the scalar operation, we have 1/2 Kx squared for the spring element. And you know that 1/2 Kx squared is a strain energy of that spring element. For matrix vector operation, we cannot really say like Q vector squared. So it becomes Q transpose times Q and 1/2. And whatever in between should be the K. And now let's check this equation. Q transpose Q, we can remove out of the integral. Very simple, because degree of freedom here, they are constant. Integration of constant, move the integration, move it out of the integral. Now B, C, B. C, of course, it purely depends on the Young's material property, right? This one is here. If you know the material property, C is constant. Make sense? For the B matrix, let's back here. Again, area of the triangle coordinates of 3 nodes. So B matrix here is also constant. And now let's check this equation. Constant. There's really nothing depends on the X, Y, or anything. So this one we can easily write as 1/2. Of course, we want to put the Q transpose and Q at 2 sides. And integration a constant over the volume equal to the volume of the triangular element times these 3 constant. Make sense or not? So we have B transpose C B times volume of the triangular element. And we know that this part should be K. Any question? Yeah, thank you. Q transpose times Q, yes. Any other question? Okay, so in terms of the volume of the CST element, you just imagine, let's say this is not triangular, but let's say this is a plane stress situation with 2 triangular elements. You have the coordinate of the 3 nodes, you have the thickness, so you can calculate the volume, right? So, and of course, in previous derivation, we use the area very frequently. So let's say we can consider for the CST element, we have the thickness H and area A. Then this K matrix, thickness times area B transpose C B. We're done for derivation of the stiffness matrix of the triangular element. What dimension of K? What dimension of K? For one element. For one CST element, what's dimension of K? Anyone? For one CST element, what is the dimension of a stiffness matrix? 4 by 4? 3 by 3. Why 3 by 3?
He's a 3 by 3 at a very hastily trying to run through the matrix math in my head.
Yeah. That we can go in that direction to check. So let's say B matrix is 3 by 6. Let me show you. Well, so transpose, right, becomes 6 by 3. What's the dimension of K? 3 by 3. Yes, 6 by 6. So this one multiplied by this one, 3 by 6, right? Oh, sorry, 6 by 3. And 6 by 3 times 3 by 6, 6 by 6. It's not 3 by 3. And also, of course, this is based on like if you really want to check B transpose times C times B, it's 6 by 6. But a simpler way, I intentionally show you this one when I ask you that question, because you can simply check here. For this element, CSC element, we have 3 nodes. Each node have 2 degree of freedom, displacement X, displacement Y. So the total degree of freedom is 6. So the K should be 6 by 6. Make sense or not? Now let's make connection with all the things we have learned so far. We start from the bar element. For one bar element, each node can only move in 1D situation. Each node can only move in the X direction, right? It can be tension, compression, but everything should be in X direction. That's why our first K matrix is 2 by 2, because 2 nodes, each node 1 degree freedom, 2 by 2. And then we expand to the truss situation, which is, again, is a system of the bar composing one structure, and it's in 2D plane. And each node now it can move in X, can move in Y. X, Y. Now we have 2 nodes, each node have 2 degree freedom. So after we expand to 2D situation, the truss situation, we have 4 by 4. Makes sense or not? 4 by 4. And then we talk about bin element. And bin element, we said, okay, each node we have displacement Y, we have rotation, displacement Y and rotation. So again, bin element, 2 nodes, each node 2 degree freedom, V theta, V theta, 4 by 4 for K matrix. Makes sense or not? Now we have CST, plane stress situation, 3 nodes, each node X, displacement X, displacement Y, 2 degree freedom. So 6 by 6. Any question about the K matrix? Okay.
Because I remember in the graph you showed that it was like 3D.
Which one is 3D?
Which
Which element?
that you like for
Okay, I think I know what you mean. You are talking about the shape function. Yeah. So here's the thing. Shape function is shape function. Let's separate these two. The whole section, the whole chapter is the plane stress. Plane stress, based on what you learned from mechanics materials, we are ignoring everything in the third direction, because I showed you in the introduction part, when the stress in the third direction, in the thickness direction, is much lower than the other 2 dimension, this one is ignored at 0. That's why we have a plane stress situation. That's why we simplify a 3D model, this is 3D, as 2D plane stress situation. So the whole chapter is about 2D. Is as an engineer, we simplify as 2D. And now we're talking about using the triangular element, and later we'll talk about using quadrilateral element. So this is 2D situation. Makes sense or not? This one is the shape function. So this is somebody saying like, okay, shape function is a function of X and Y. And if I ask you to imagine how does this shape function looks like? Shape function, this plane is a function of X and Y. And if I ask you to plot the shape function, let's say how it should look like. So this third axis is not really like Z axis in the 3D space. Third axis is just shape function. Shape function as function of X and Y. So that's why you have, let's say, shape function at node of N1 is 1 at node 1, 0 at node 2, 3. Shape function N2 is 1 at node 2, and 0, 1, and 3. Shape function N3 is 1 at node 3, 0, and node 1, 2. And because shape function is linear in X, linear in Y, so it becomes a plane. It's a plane. This does not mean that we're dealing with 3D. This is simply a plot of shape function. Shape function as function of X and Y. The third axis is shape function. Doesn't mean that we're dealing with 3D problem. This is completely 2 separate things. Sorry, I cannot hear it.
Are we expected to understand those graphs? Like
yeah, of course. You need to understand everything in this class.
No.
Yeah.
good to like read the graphs or maybe like graph them ourselves?
Read the graph. I'm not gonna ask you like explain what is shape function during the exam, right? Because our exam is really like calculation, but you do need to understand the shape function to solve our problems, right? You need to understand shape function to solve our actual problems. Yes. Any questions? Any other questions? Any other questions? Okay, let's continue. So now we have the K matrix, right? You know the coordinates, you know the multi-property Young's modulus Poisson ratio, you have the K matrix for our CST element. The next thing is that KQ equal to F, because all our previous calculation is based on, we already know the nodal degree of freedom, but in real situation, we know the structure, we know the material, we know the force applied. We don't know the nodal degree of freedom, so we calculate. So now KQ equal to F, we know the K. Now we need to figure out what if there's a force applied, how to put in the F vector. And then we can use inverse of K times Q, sorry. Yeah, equal to times F equal to the Q. So I think this is in the textbook chapter 6, section 3.4. Externally applied force. The first one is the similar situation. What if we have the concentrated force applied? So let's assume that concentrated force applied at nodes. Let's say in the 2D space, XY coordinate, we have a general CST element, triangular element. And we have 3 nodes. First node can be any node, but it has to be counterclockwise if you want to use the equation we derived in our class. And let's say at each node, we have the force applied in X direction and force applied in the Y direction. Let's use red color to represent the force applied in the X direction. So F and node 1 in the X direction. F and node 2 in X direction. And F and node 3 in X direction. And also, we have the force applied in the Y direction since it's a 2D problem. F and node 1 in the Y direction. F and node 2 in the Y direction. F and node 3 in the Y direction. And of course, some of you may ask, what if there's a force, considered force applied at some random point? If there's a force applied at random point, it must be a node. You need to generate extra node here. So let's say if there's a node here, there's a force applied here, then you need to separate at least to 2 triangular elements. Make sense? That's why when I mentioned like let's say using FA in different area, let's say if you have a scan of the jawbone and it has too many small patches, why do we need to smooth the structure and make it smaller number of patches? Because if you have smaller patches, every point need to become a node in FEA analysis, which is too much. That's why you need to make it smooth and actually make the element larger, the patches larger, which is maybe not the same as what you guys think. Like everyone always feel like, oh, if you want to get better results, always refine the mesh, smaller elements, more elements better. But you need to know that in real situation, first, it's not necessary. Second, it's not doable. So now, if this is a similar situation, if we have the concentrated force applied at 3 nodes, so we can have the K which in this situation, of course, CSG element is 6 by 6. Q, we have the 6 components, displacement node 1, node 2, node 3. And for the force vector, of course, displacement at node 1 in the x direction should be corresponding to the force at node 1 in the x direction. Displacement in the y direction, node 1 should be corresponding to the force at node 1 in the y direction, right? So, of course, for this similar situation, we can write as f node 1 in x, 1 y, 2x, 2y, 3x, 3y. We're done. So of course, this is a similar situation. And if you remember in the beam chapter, we talked about what if there's a distributed force applied on the beam. And we did the derivation, like how to, this is separate section, ask you guys to find the work equivalent nodal force. So if you have a beam and you have a distributed force applied on the beam, we need to use integration of shape function times the distributed force and it integrate at each node and becomes the equivalent nodal force. Remember, we also had a homework. If you have the interchange distributed force, we need to do the calculation. So let's put a situation here. What if we have the distributed force on the edges, element edges? Let's use a similar situation. What if it's uniform distributed force? In 2D space, XY coordinate, we have a triangle. And node 1, node 2, node 3. And let's say we just use edge 1, 2 example. It can be edge 2, 3, can be edge 3, 1. It doesn't matter. Let's say on edge 1, 2, we have the uniform distributed force. It can be in any direction in the XY plane, but to put in the vector, let's simplify as the x component and the y component resolve into two xy coordinates. So let's say for the distributed force, the x component let's use tx, and y direction ty. It doesn't look like the uniform distributed force, but it just imagines uniform distributed force. So it's the force applied on the edges. So just imagine, yes, it's 2D problem, but still has a very thin thickness. So you can just imagine what if there's a force applied on this edge. There's a small area here. There's a length of this edge. There's a very thin thickness. So there's a small area. And I can apply, let's say, this is compression. I can apply tension. I can apply shear. So let's say tension compression is perpendicular to this edge. If I'm having this in the perfect xy coordinate, right? Tension compression could be considered as the ty here. I can apply shear. Shear could be considered as in the, if this is x direction, tx, right? So it's really applied on very this thin area. So now let's assume that the force Tx, Ty, they are the uniform distributed force along the edge. So the unit we normally put as Newton per area, meter square. And if we assume that the edge length of the 1, 2 is L, thickness again H, again, standard procedure, we still need to do the integration. So integration, shape function times uniform distributed force, and here Tx is constant, dx, right? And integration, if you use the N1, it becomes the equivalent nodal force at node 1. If you use N2, it becomes the equivalent nodal force at node 2. And of course, since it's distributed on the edge, we can use the 1D interpolation, which is very simple, 1 minus s and s. So standard procedure, we do need to use integration shape function times distributed force dx. This is for 1D inflation. If the force is only applied on one edge, this is 1D inflation. And of course, mathematically, this is not that complicated because integration 1 minus s times a constant, integration s times the constant at 2 nodes, there should be no difference, right? Or you can just simply understand it as like, if you have uniform distributed force on one edge, there's no reason one node get a higher equivalent nodal force in the other node. Makes sense or not? Because it's uniform distributed. So a simple way to understand is that you calculate total force applied on the edge, divide by half. Actually, so this becomes easier because in the bin, it involved v and theta, right? And here is displacement x and displacement y. And if you have uniform distributed force, there's no reason one node get a higher equivalent nodal force than the other node. So the easy way is that what is the total force applied on this edge divided by half. But of course, this is just a based on our understanding. If you check textbook, they have a detailed derivation, integration shape function times p, or tx, ty here, and you get everything, right? So let's say total force in x direction. Let's use different color. What is total force in x direction? If Tx is given as Newton per meter square and the edge length is L and thickness is H, what total force? Yes, thank you. And similarly, the total force in the y direction should be Ty L H. And for this KQ equal to F, well, this part is always the same. I don't want to repeat this part. We just simply write this part, how to write the F vector. So here I can write as F1x 1y, 2x 2y, 3x 3y should be equal to L H half. Since it's only, our example here is only on edge 1, 2, so it's only node 1 and node 2. Tx, Ty, Tx, Ty. The rest, the node 3, 0, and 0. But of course, you can check the textbook for the integration shape function times discrete force. And if you use original the definition equation to derive, it can also derive what if the discrete force on the edge is not uniform distributed. If it's, let's say, I give a function fx, you can do the integration, right? Or it's linear change. But in this class, I'm not gonna go that crazy. We only, let's say in the homework exam, you will only see uniform distributed force. So you can use this equation directly. And as I explained, this is purely based on understanding. For the derivation part, check textbook. Or if you have any question about textbook, come to my office hour. So this is uniform distributed force over the edge. And the third one is, what if there's a uniform distributed force of the volume? Because let's say in some situation, if the weight of the structure cannot be ignored, and the weight is not a force applied on any edges. It's not simply a force applied on any edges. It's a uniform distributed force of the volume. Make sense or not? So we need to consider, okay, in that situation, how to put it as equivalent nodal force as 3 nodes for that triangular element. Or let's say if it's two metal and there's magnetic force in between. And that one is also, again, not a concentrated force applied node, or it's not a force applied on any edge. It's, again, considered as a uniform distributed force of the volume. So in those situations, when you consider how to put it as in the vector nodal force, equivalent nodal force, how to do that. So the third one is a body force. Mathematically, you can consider it's a uniform distributed force of the volume, and it could be things like gravity or magnetic force. And since it's a force, uniform distributed force of the volume, the unit, it should be Newton per meter cube. And of course, we have the area of the triangular element. We normally use A. Again, standard procedure, integration of shape function times uniform distributed force. And you can get the equivalent nodal force at each node. So basically, our shape function, we already derived. Let me show you this graph again. Shape function, we already derived in the previous class. Or if you want to see the plot of shape function, again, this is the plot of shape function. So you integrate, let's say at node 1, you integrate n1 times the distributed force. Now here, our distributed force is a constant. And then you get the equivalent nodal force at node 1. Mathematically, again, similarly, integrate n2 times the distributed force, xy, and here is constant. Over the whole area, you get the equivalent nodal force at node 2. Integrate shape function n3 times distributed force. You get the equivalent nodal force at node 3. Again, textbook had a detailed several page detailed derivation, but again, let's just based on our understanding. If you have a uniform distributed force over the volume, again, there's no reason one node get higher equivalent nodal force in the other two nodes because it's uniform distributed. If it's not uniform, you need to do integration, right? I give a p function as xy. Then you need to do the integration. But if it's uniform distributed, there's no reason why one node get higher equivalent force than the other two. So a simple way is that based on understanding, to skip all the derivation part, you can check textbook for derivation. We can just simply calculate total force in the x direction, total force in the y direction, and equal distribute to describe to the 3 part, and each node has 1/3. So again, the total force in the x direction should be bx times the volume, right? So we already know that thickness is h. So it's b x a h. Let's add the thickness here. And similarly, we have the total force in the y direction should be by times area times the thickness. And for the vector, we can write as, again, these components, 1x, 1y, 2x, 2y, 3x, 3y. Any question? So basically, let's say if I consider this vertical direction is the y direction, and I only consider the weight of my triangular element, then it means that, okay, this x, they become 0, right? And this b y a h become the weight of the triangular element. If let's say it's magnetic material and I have another magnetic material in the x direction, then it means that these 3 components become 0, and whatever force you divide by 3, it becomes in the x direction, force in the x direction. And of course, if you have additional force applied node, additional force applied on the edge, superposition, you get a final F vector. Make sense or not? Okay, so now this is the conceptual part. We have 5 minutes, right? Do you want to continue or study the next class? Next class? Okay. We'll talk about example in the next class. Thank you for coming and have a great day.
What do you homework due later this week for the second one?
Yes.
And I was trying to figure out how exactly you approach it. So I get what you do to find UX and V or UX, Y, V, X, Y, all that the strain. But in order to get, like, am I on the right idea here? Basically using this old method to get the displacement of 2, and then from that.
Yes. Yes.
Okay.
This is correct, because everything that I know that's they're gone. Only 2. Yeah.
Okay. Because when I was doing this, I don't know if I'm doing something wrong, but I ended up basically getting that it was 0, which I feel like is
Wait. What the question asked?
find out U, X, Y, and V, X, Y, and then the strains. So I got the displacement at node 2, assuming 1 and 3 aren't moving.
Okay.
And so the displacements at each node then
Okay.
be this.
Okay,
And then so I found, the shape factor
yeah,
and all those constants, and then when I plug in, it ends up, everything basically cancels to get zero, which doesn't make sense, I feel like.
M2 equal to 0.
Yeah. Because F2 was 0, B2 was 0, and then C2 was 0.
Can you screenshot this one and email me? Because I need to
It's really, just like that.
this part, this part.
Oh, yeah, this part, yeah, sure.
Yeah, yeah. I'll check in detail later. Yeah, I'll let you know. Hi.
Hi, I can't see your office hours because
Yeah.
Canvas is down, but I
Yeah.
would always look at my app because for the project, like, it always says 0 stresses. Like, and it happened for the homework too, like, I could never get stresses in my thing.
I need to check. Is this running the input file?
No,
This is, can you come to my office hour? I need to check step by
yeah,
step.
when, today?
2 to 4.
Okay, today,
Yeah.
where?
Do you know MAC?
Yeah,
106.
okay,
It's either in 106 or 126.
okay,
Because if too many people, I need to move into the lab because I don't have enough chairs in my office.
okay, 106 or 126?
Yes, yes, yes.
2 to 4.
Yeah, yeah,
Got it, thank
yeah.
you.
Thank you,
Thank you.
thank you.
First, I sent an email about the,
I read that
Okay.
before the class.
and then, second, I wanted to ask, so on the homework 6, I understood this was the method, the one with the stiffness matrix.
Yeah.
And you could just solve it like a normal setup. I wasn't sure if what was meant by a second method.
Yeah.
I understood it probably had to do with the shape function, but I didn't quite gather what I was supposed to do after.
So you find the nodal degree freedom. Basically, based on nodal degree freedom, you can calculate strain.
Okay, so calculating the strain,
What's the question ask? The question ask calculating the strain, right?
it wants the,
This is the homework.
yeah,
This is the homework.
this is the previous one.
Okay.
Yes.
Okay. Bending moment shear force. We ask about 2 different methods calculate bending moment shear force. So you need the first, you have the K for this one, you have K for this one, you do assembly, and then you apply boundary condition, it becomes 1 by 1.
Mm-hmm. Yeah, that's this one here.
Yes. And you solve for that one, and that is only non-zero the degree of freedom.
Yes.
And then for the bending moment shear force, there are 2 different methods. One is based on the, I can show you here. This is the second method, this is the first method. So you have
Okay.
everything solved. You have the K. You can solve the bending moment shear force. Second method is based on definition. Bending moment, second derivation, shear force, third derivation, and you can calculate the bending moment shear force. So these are 2 different methods.
I
For-
see. So then,
That's it.
so on this, so then, because the force on the picture is only applied over one portion,
Yeah. mhm.
then do. does this
You have
equation-
you have 2
you
elements.
have two
This is
elements, you have
one element.
This one, and then you're doing a superposition with the other one.
Yeah. Yeah.
Okay, and then how would the concentrated moment apply to that one?
So one element, and you assembly.
Mhm.
You assembly, and for the force vector, equivalent force, and plus whatever applied here, like
Okay.
the extra thing applied here. So that is your question here, how to write this vector, right?
Yeah.
Because you have the one part, so we only need the one that corresponding to theta 2, so it's a C2. So from this uniform distribution force, you can find equivalent C2 plus the extra C2
I
applied,
see. Okay.
and it becomes the one in the force
Okay,
vector.
so this becomes equivalent when you do the conversion with the formula.
Oh, no,
Or-
that is
no,
not,
this is with the, this is,
that is only for solving nodal degree freedom. After you solve
Right.
nodal degree freedom, it does not depend on the external applied force, then you purely use these 2 methods. So basically,
so I,
level K times Q equal to this one, or you have this one. So after you solve nodal degree freedom, you don't need to consider like C applied equal nodal force. C applied and equal nodal force
okay,
is
so I-
only for,
so then I guess I'm confused by, because the element, so these are applied for these two.
So
nodes
no,
that seem-
no. Let's say you already solved for the theta 2, right? That's the
yeah.
only thing you need to solve. So eventually you have V1, theta 1, V2, theta 2.
Oh, okay,
Make sense
so
or not?
the theta 2 is equivalent across the whole.
No, now you want to calculate this one. So basically, for this element, you have
Oh, okay,
theta
'cause it's
1.
just for that one element.
Yeah.
And, oh, I see, I
You
understand.
have theta 1. So basically, you have only this one as
Theta 1. so
Yes.
The theta 2 from the previous, or from the whole thing becomes theta 1 in this.
for this
Because
element.
it's just for that element.
Yeah.
Okay,
Now you are trying to find out the Bending shear force at this node. So it's the second node of the second element.
I see, yes, okay, now I
So
understand.
you need to write this one for the second element, and this becomes the second node for the second element. And the same thing here. If you, for the second element, you write this expression, and you write this expression and this expression, you plug in s equal to 1. It becomes,
Yeah, because it's the far side of the
Yeah.
shape function. Yeah, okay,
Yeah,
yes,
yeah.
okay, perfect.
Yep,
That makes
yeah.
sense now, thank you.
you're welcome.
Sorry, I just have one more question.
Yeah.
For the exam next week, so is it just all the lectures since the previous exam?
Yes, yes. It's not a cumulative, so
It's not cumulative?
No,
Okay,
no.
and so is there any abacus stuff on there?
No.
Or just like all the beam stuff and like the lectures?
we don't test anything related to abacus on
Okay,
exam.
So just those lectures. All right, and
Yeah.
are you gonna post the homework keys for the?
Yes, I will do it tonight.
Okay,
Yeah.
all right, thank you.
You're welcome.